Now, of course, some of you must wonder that what happens to when the second order derivative becomes 0? When the second order derivative of the total potential energy with respect to the variable in the problem becomes 0, we call it neutral equilibrium or neutral post-Berkeley. Now, let's look at these to understand the meaning of 3 of them. In the energy approach, we will use this expression, this condition, to find out the critical load. But unlike the force approach, the energy approach actually can tell us what happens beyond the post-Berkeley. If you remember last week, this is what we talked about. When we look at the force and the deflection curve, right? And by considering, for example, there's a column, and you start applying the force, which is something like this. Suppose this is a force P. And at the beginning, you're going to increase the value of the force, starting from 0 and gradually increase, until it arrives what we call the value of critical load. At the moment, the force equilibrium can tell you what is the value of this critical load force. But that's all the force approach can do. Beyond this point, you can only use the energy approach to determine that whether the structure is going to be stable in the post-Berkeley behavior or is unstable. Now, what is the example for the stable post-Berkeley? For instance, you have several examples before. When we call the stable post-Berkeley, that means beyond Berkeley, the level of the force should be greater than the critical load. That means it should be something like this. If it goes up like this, then we call it stable. If it goes like this, we call it unstable. So the power of the energy approach is really lies in the post-Berkeley behavior. Only the energy approach can tell us whether the system is going to be stable or not. So let's come back to the example and to apply it. Then you will know that how we can actually use it. So first of all, you can relate these two, or you can just differentiate these two to use, or you can use this one. Either way is fine. You can let this to be 0. Suppose we use, because we have expression of capital pi, right? Then we can use this one to find out. And because we said the derivative of the total potential energy must be 0 with respect to theta must be 0, this is how we're going to find it. And which means you're going to differentiate this expression. That is the difference between strain energy and external work. And strain energy has the expression of 1/2 of Ks times theta squared. That's strain energy. What is external work? External work is P times L times 1 minus cosine theta, right? So here, I did nothing but just substitute the expression that we found from last page. So the first term is strain energy. This one is strain energy, and this is external work. Go back to here. So this is what we found. So we just plug it in. And then we differentiate the whole thing. So here, so what do we get from here? If you differentiate this, you're going to have, the first term is going to be just Ks times theta, right? What about the second term? The second term is going to be negative P times L times sine theta. Is that clear? Right? Yeah. And this should be 0. And if that's the case, we will find out the expression of P. And in this case, P equals to PCR to be what? We just move, turns around, and it actually turns out to be Ks times theta divided by L times sine theta. And if you care to compare this expression with the expression we found from the force approach, so what did we find? It's the same, right? And of course, they should be the same, because the final answer can be found by different approaches. Doesn't matter whether you use the force approach or the energy approach, the answer should be the same. So similarly, if we apply small deflection assumption here, and you know that P approximated to this expression, which is by letting theta to be theta itself and sine theta to be approximated to be theta, and that will cancel out thetas in both numerator and denominator. So this whole thing will simply just become Ks over L, and that is the PCR for this problem. Of course, still the same as the one we found before by the force approach. Now, you must be excited about what happens during the post-buckling behavior, right? So from here, we just determine the value of the critical PCR, which means that in this figure, we know the value of PCR to be approximated to Ks over L. So this is the value we have found, but we want to know that what happens beyond this point, and we can use the energy approach to figure this out. So let's go to the next page, which is page 14. We're going to look at the second order derivatives. You already had the first order derivative, and how do we get the second order derivative? The second order derivative is this. Differentiate the whole thing, the expression of total potential energy with respect to theta again, and that expression is right here, which is this expression. Differentiate the whole thing with respect to theta again. So what do we get? You're going to get this. The first term will become just Ks, right? So this will just become Ks minus P times L times cosine theta, right? Cosine theta. So let's write this whole thing one more time. This is the second order derivative. And if we use small deflection, we're going to say small theta. If you use small deflection assumption, and this expression can be approximated to just Ks minus P times L, because cosine theta approximates to unity, right? Now, let's use the energy approach to determine the post-buckling behavior. When the second order derivative of the total potential energy is greater than 0, that means Ks minus PL must be greater than 0. That means what? That means P must be less than Ks divided by L. If that's true, then we say it's stable. Now, if you look at this expression, you will know that, of course, it makes sense, correct? Because Ks over L is the buckling law. So what this result says is mathematically, you can use the second order derivative of the total potential energy to formulate the stable post-buckling condition. And this is a super simple example. And here, all we are saying is just to make sure that when your force, applied force, is less than the critical force, and of course your structure will be stable, and vice versa. If this second order derivative is less than 0, and that means Ks minus P times L must be less than 0. That means P must be greater than Ks over L. Of course, this means it's unstable. Right? That also makes sense. And when the second order derivative becomes 0, that means this is the neutral equilibrium. That means P equals PCR. All right. So this is example.
One question, Professor.
Yes.
Shouldn't it be the other way around? Because just looking at the graph, greater than PCR means you're in stable condition. Smaller than PCR, you'd be in unstable condition.
What did I say? Did I copy it wrong? Which part is unclear to you? Which part? Stable or unstable?
Sorry?
Stable or unstable?
No, I was just looking at the graph, and stable is above PCR, which means should be greater, and unstable is below PCR, which means should be less.